So, hi everyone. My name is Ofri. I'm the VP Research at Lightrix. I'm happy to be here today to talk about turning GANs into useful consumer products, specifically on mobile. So we'll cover a lot of things, how GANs are enabling a lot of new creative flows, and all the things that we found along the way that in building a feature that is very centric around GANs in face editing. This is more of a talk about the way and the insights that we got. It might pique your interest in a couple of issues and problems for further research down the line and give you some insights on how to solve some of these problems. It's ranging from data, which is always important in any machine learning model that we build, through the trade-offs between quality, control, and expressivity, and all the way to how we got huge neural networks to run on mobile devices and pretty fast too. So GANs are driving a lot of new creative flows. About 3 years ago, we actually introduced our first GAN-based feature into a Lightrix product. It was in-painting of images. It was arbitrary images, arbitrary masks, and it was just better than any other content-aware in-painting algorithm that we had before. You know, it's better in completing curves, in all the small details. And it was a long road to get it to work as a GAN in the highest quality and on device. But since then, when in-painting and super resolution were the thing in GANs, I think the area, like the field, exploded. And today we have a myriad of applications and creative flows all around, you know, in academia, on the web. It's even things that are becoming more and more available, not just to us researchers or techies, but it's more popular science and available to artists and available to creative types and creators. So we wanted to see how all these things can be relevant to us. Now, if you don't know us, then at Lightrix, we build apps for content creation and content editing, for mobile, for web, for all kinds of creators, people who are living on social media and people who are looking to really up their game in terms of the creations that they make. We have a lot of users from a very wide spectrum of skill sets, from beginners to really pros. And we try to enable them to do all kinds of amazing things to create better digital media and just make it easy for those who can already and make it possible for those who couldn't before. So we thought, what was the one thing we want to take right now? And I think that, you know, face editing was always a centric part for GANs and in research and academia, because, well, we have a lot of faces, and style GAN using FFHQ was really one of the pinnacles for research around GANs and high quality images. And on that area, I think we've all seen what GANs can do, right? We take an image, we find a way to create it in a latent code, either by optimization or by an encoder. I'll talk about it a little bit later. And once we have a latent code that regenerates that image or something a little bit similar, we can use even linear traversals in the latent code to generate all kinds of images, right? So we can create pose changes, we can create smiles, we can create, you know, aging, a lot of stuff. And in Lightrix, one of our biggest products is actually Facetune. And in Facetune, what we wanted to build was a new feature that allows ready-made presets for users to add all kinds of makeup, but it's not just makeup, it's a little bit of the lighting, it's a little bit of you know, toning. And we wanted to do it on mobile devices, and we wanted to enable, on one hand, ready-made presets, but on the other, still leave control to the users to choose how much of the effect they want. So traversal by slider is something that is pretty hard to achieve, since traversals are, you know, the addition to the latent code is linear, but the traversal result is non-linear. So that was basically what we wanted to achieve and what we wanted to build. And I'll tell you all about all the challenges and all the things that we learned along the way. So just to mention, this is, of course, a huge endeavor with a lot of teammates and teamwork. And aside really from the researchers you see here, there's a lot of people, designers who worked with us on it, and product engineering people that helped along the way. So let's talk about data a little bit. Okay, data is king is something that I always find myself saying. And we all know, right, that data matters. Data is important because what we train a generative model on is basically what they can create. They can interpolate, but if they don't see something at all, if something is really out of domain for them, then the limitations are already there in what they can express and what's easy to actually get from the latent code. And better data means better models, but what is better data exactly? So we found actually that there are two main areas where we can talk about better data. One is the photographic domain, right? So when we talk about StyleGAN on FFHQ, so FFHQ is pretty biased. It's mostly pro cameras. There are a lot of mobile cameras too, but not enough. There's all kinds of things that are happening there that are not the real world, or at least not for us. So there's things like more noise and contrast and bad lighting. And it's not by chance that actually people use StyleGAN in order to improve images, because it naturally goes and tries to create images which are sharper and better lighted and so on. So once you get a dark image because someone took a photo when it was dark, then you need to adjust for that. But also more fine-grained issues like focal length and what faces actually look like when you build a 3D model. So if you think about focal length, then an example here is, this is me. But this is me using selfie, which is the most common portrait of a person taken today in the world. But this is a selfie, and this basically is me again, but using actually the back camera of my phone, standing a little bit farther away and cropping to the face region. So when you build a 3D model of a face, then you can correct for that. You can look at the perspective warp that you get, you can change it, and you can, if you're talking about even GANs of neural rendering fields and all kinds of things like that, you can fix for that. But if you're talking about a GAN that generates just images, then these two faces are still, totally viable faces that the generator needs to know how to create. And in one the ears are more looking, and one the nose is bigger, so you need to adjust for that. And the other way is actually what it is that that the generator sees, because we want to build something around makeup, and we want to build something around better looking images and better scans. So we need to show more data to the generator and to all other components that we use along the way. So that's one thing, and I really urge people to look at the models that they get off the shelf. It's great to use them, but they have limitations that sometimes you blame your pipeline or algorithm, but sometimes it's just the data. More important is actually quality and control. What we set to achieve was identity preservation. We wanted to express makeup-like effects, but we wanted plenty of them, so we wanted expressivity, and we needed to let the designers, for the users it was just presets, but the designers needed to decide if the lipstick is more bold, if there's more shine, if something is more specular or not. And we had to solve all these types of problems. So in identity preservation, actually, what we had to do is look at how we can recreate the exact person. And the exact person is not just them. Sometimes it's even, the glasses that they're wearing. It's, all kinds of small details that people consider themselves, because we try to create, the best version of yourself and not some other version of, someone who's maybe a little bit similar to you. So when looking at all kinds of solutions that are used today in most research, there are encoders that try to find the latent space, W space in StyleGAN, and there are fast ones. There are more, better ones with a lot of effort put into them. But basically, we couldn't look at anything that was really long. We needed to find something that was fast. Encoders into the latent space of StyleGAN are pretty fast, but they're very limited, both by their training and by the domain of the generator. Latent code optimization, just trying to optimize the latent code, works better, but it's very slow and it's still limited by what the generator can create. You can do generator optimization, or what in Danny Cohen-Ohl's team call PTI, where you redraw the target after shooting the dart, as they said it, and that works really well in getting identity preservation at all costs, but it costs quite a lot of time and really can't run on a mobile device. So we had to go, that was kind of a choice that we had to make, to an encoder-decoder strategy and architecture where the structure and the preservation of identity is baked in. Right. So this is basically what we built. We built an encoder and decoder where we have two latent codes, both for structure preserving and for texture controlling, where texture is the makeup. And for the auto encoding, we used L1. For all the rest, we used patch discriminators and face shape losses around our face model and 3D-MMs. So we can actually get very good reconstruction, and used all kinds of augmentations and mixing of latent codes in order to train that system. I won't go into details there, but I will say that choosing an autoencoder with such strong constraints on structure actually makes stuff like smiling pretty hard, because it really, you need to recreate the smile out of not just the latent code, but also the structure and the latent code. So that, of course, when there are no teeth at all, it becomes much, much harder. So that's not really working. But more than that, we actually wanted to get fine-grained controls of what it is that we can find in the latent traversals. And it can't really work if we do simple classifiers like an interface GAN, or even use CLIP, which again did not see very fine-grained examples in the data it was trained on. So we are now actually trying to use pairs of original images and rendered images, where we can control every little bit of addition of makeup that we do. The only thing to notice is that actually when we render it, it doesn't always come out very realistic. So we need to adjust for that and use augmentations in order for the discriminator to adjust and compensate for it. So last but not least, taking all of this and making it work on a mobile device is really something that is not trivial at all. So if this is the structure, we have the encoder, which is actually pretty fast. It's regular convolutions. It's mostly dependent on resolution and number of channels, and it runs only once, because once we get the latent code, we don't need it anymore. The generator, right, the decoder, is actually the big part to look at, because it's slower, it has modulated convolutions, it's much more complex, and it needs to run a lot of times per each traversal. So there are a lot of works out there You can look at works from, Han's lab at MIT, GAN compression and stuff like that. But most of them are kind of missing the point on big models that are not classification models, but actually image-to-image models that are really at the edge of the capabilities of mobile devices. It's a lot of times about memory. It's a lot of times about swapping out different parts of the model. So what we actually learned, and I can maybe give that as an insight to anyone else who's trying to achieve something similar, is try and using a big teacher, but dissect it in order to get a smaller student and then train it, because it really helps in GANs, not just in time to train it, but also in quality. And when looking at the architecture, look at mobile specific things like the type of ops that you use. If you want to use specific, accelerators like the neural engine on iOS or Qualcomm's solutions, then you really need to choose the specific ops that you use in each layer, and be concerned with, again, memory more than most. We actually built an automated system where researchers can try different architectures on a lot of devices and get in real time the runtimes for them so that they can optimize for it. And as you can see, it doesn't come for free. If on the top left we get the original input image, then the biggest model that does not work on a mobile device is next to it. And it's pretty good. I'm not sure if through Zoom compression you can see the fine details, but in the hair and all kinds of things like that. This is the best model that actually works on device. And these are models that are even smaller and faster, but they have all kinds of artifacts around the shape, around the hair, around small details, waxy, smooth skin, and so on. In terms of runtimes, we actually found, like I said, that ops really, really matter. All times in milliseconds. The smallest model, which was not the greatest, was sub-second for the encoder, and 2.3 seconds when unoptimized for a specific ops. But the same number of parameters for the same model was really 134 milliseconds for the encoder and sub half a second for the decoder, and also for a bigger model, which is the one that we actually use today. So I just want to say that this project is really something that was great to work on, because we do a lot of things at research, and it started like in the rubric of GAN-based editing. But because we put in a loss for the shape of the face, it was also the face modeling team, because we had to build a render pipeline to create the makeup to control the latent traversals. Then it was also in rendering. It was a lot of the core things that we do around compression of networks and around optimizing it for edge devices. It was really an all hands on deck kind of thing. So, yep, thank you for listening to the talk, and hope there.
Great, thanks. It was great talk. We have probably one question or two if we have time. So the first one, how do you measure the quality of the results, both of reconstruction and of the edited images? Of course, this is a subjective thing with images. So what is your solution on that?
Right. So this is one of the hardest thing, actually, because a lot of people look at FID for measuring GANs, and FID is really great when you're at very low performance, low quality results, and you're improving it. But once you get to a certain threshold, it really doesn't tell anything about the story. So what we are doing is a couple of things. One is just manual labor that we actually automated as much as possible to create very, very distinct and very standardized reports of how everything looks, so that both the regular designer team and other crowdsourced people can look at and grade. But other than that, we incorporated several losses for specific things that we saw that we needed to preserve. Like if we wanted the nose shape to be preserved, then we added a very fine-grained nose shape estimation and saw that it was just preserved around the changes that we make in the architecture as we go along.
Okay, another question. What would you say are the main gaps between training a generator on better data and achieving all your goals of quality and expressive power of network?
Right. So in general, I think that data is, like I said, data is king, and if we show different types of data to the model while training, we get a lot of improvement already in the latent space. What we saw initially that we blamed kind of our ability to control the model in all kinds of things, like for instance, if we couldn't get a specific type of lipstick, like if we couldn't get black lipstick, then we said like the latent space is not good enough. And we even tried things that are very popular and common now in research teams, to use CLIP in order to guide our latent code traversals. And CLIP, if you tell it to have a goth look, then it actually adds black lipstick and quite a lot of other things as well. So it saw black lipstick, but if you tell it just black lipstick, then it doesn't work so well. And which is why we actually got into rendering pairs of samples in order to try and get better control over our latent space traversals. But like I said, that only solves maybe the expressivity of the person who wants to say what it is that they want, the designer and later on the researcher. If a model did not see these disentangled examples of people with black lipstick but without the goth look, then it's very hard for it to find disentangled representations and in the latent code, as well as in whatever is coded in the layers in between in the generator.